Okay, we will start with 15.6, 15.8, I mean. 15.8, it's a triple integral in cylindrical coordinate system. Now we have double integrals in cylindrical, right? In polar to be more precise. Right now we have triple integrals in cylindrical coordinate system. Now the idea is I want to see this from two points of view. The first point of view is that in the past, when we did double integral with dy dx, for example, we change the dy dx becomes, call this d1, becomes r dr d theta. Okay, so dy dx then becomes r dr d theta. Okay, now what happened in this triple integral now? It's basically the augmentation of that when we have the triple integral over a region E1, let's say of f dz dy dx, for example. Then we convert the dy dx part into r dr d theta. Okay, so the idea is still the same. So the xy coordinate system, the rectangular coordinate system on xy plane, now becomes a polar coordinate system in r theta. Okay, now of course then we can pull that r to the middle. So this is f times r dc dr d theta. Okay, and that's basically it about this section. That's basically it about this section. Now, of course, we will do examples. Let's take a look on some example. Where's my notes? I will spend some time, maybe around 15 to 20 minutes for 15.8 and 15.9 to do problems. And then maybe not 20 minutes, maybe 30 minutes. And then I will do part of 15.10. So you will see if we get to, let me screenshot the exercise set for 15.8. Now we have this before, at least something similar to this. We have this. Okay. Now my assumption is you already learned from last time. We talked about this in chapter 13, I believe, or chapter 12. Chapter 12. I think this is at the end of chapter 12. Like at that time we learned from converting from rectangular coordinate system to cylindrical, vice versa, and from cylindrical to rectangular. In 15.9, the foundation will be from rectangular to spherical. Okay, and spherical to cylindrical also. Anyway, I will not go over this anymore. I assume you know this. Otherwise, we will do some problems. We will pick this up along the way. Okay, but in my suggested homework later on, I will ask you to review, to do some problems from here. Okay, let's go on to the integration parts, the one that we need to do integration. Let's say we do number 16. Number 16, sketch the solid whose volume is given by this integral and then evaluate the integral. Let's do the evaluating first. Let's evaluate the integral first for number 16. This is equal to integral from 0 to 2, integral from 0 to 2 pi, and then r dz, that's independent of z, huh? So that's basically r times r d theta dr. Can you follow me? When I integrate, notice that this is integrating with respect to z, right? So we don't need to worry about this r. We can just do it later, right? But when you integrate respect to z, integral from 0 to r dz, that's the length of the interval, right? Okay. Now then I go on. It's independent of theta. So this is integral from 0 to 2 r squared dr, integral from 0 to 2 pi d theta, right? Because they are separable and the domain is a quote-unquote rectangle. This becomes 1/3 r cubed from 0 to 2, and this is 2 pi. This becomes 8 over 3 times 2 pi. That's 16 pi over 3. Oh, that one is easy. Not too hard to integrate this. I think the challenge is, can you sketch the solid? Can you imagine what is the solid look like? Okay, let's see. So we notice that the z is from 0 to r. C from 0 to r. The theta is from 0 to 2 pi, and the r is from 0 to 2. Okay, so for this part here, it's basically on the polar part, you will see that's basically a disk with radius 2. That is a disk with radius 2. It's the r theta. Okay, now then how about z equals to r? C equals to r. So if this is r, this is c, that's from 0 to 2. It looks like this, right? Okay. Now then if I rotate that with respect to r, with respect to z-axis, then it looks like this. Can you imagine that? Actually, this is not correct. It's like it is like a cylinder, a circular cylinder, but then you cut the cone away. You cut the cone away. Okay, that's a circular cylinder, but you cut the cone away. Okay, now the radius of this cone is the radius is 2, and the height is also 2. Okay, so if we compute this geometrically, and then the volume is equal to the volume of the cylinder minus the volume of the cone. Is that right? The volume of the cylinder is pi r squared times the height minus the volume of the cone is pi r squared times the height over 3. Why I feel something not right? Two pi r squared. Am I missing something here? Yeah, this is 8 pi. minus 8 pi over 3. Oh yeah, that's right. This is 24 pi over 3 minus 8 pi over 3. That's 16 pi over 3. Oh yeah, that's correct. Duh. Okay, I thought I was wrong. So you notice that the way I did the integrations, right? I get 16 pi over 3, but when I look at what this solid looks like and what's the volume, I compute that using geometry, I get the same result. Okay, let's try number 15 too. Why not? Number 15, let's do the integration first. So this is integral from negative pi over 2 to pi over 2, integral from 0 to 2, and then r times r squared dr d theta. Okay, notice that the inner integral, the integrand has no z, right? So the inner integral with respect to z will just be the length of the interval. Now then, this is integral from negative pi over 2 to pi over 2, integral from 0 to 2 of r cubed dr d theta. Oh, that's rectangular domain, and the integrand is separable, so that's integral from negative pi over 2 to pi over 2 of d theta. You can just call this pi if you want. Okay, and the integral from 0 to 2 of r cubed dr. Now this is pi, and this is 1 over 4, 2 to the 4th. What's that? That's 4, huh? That's 4 pi. Now can we sketch the solid? Can we sketch the solid? Now on r theta, the radius is from 0 to 2, but the theta is from negative pi over 2 to pi over 2. So it looks like this. The semi-disk, half of disk with radius 2, right? From negative pi over 2 to pi over 2. Okay, and then as for the z is from 0. This is r, this is c here. It's from 0 to r squared, like that. Okay, so if I rotate that, it actually looks like this. But only half. It's like half of the cylinder, but then we cut the paraboloid away. Okay, half of cylinder, then cut the paraboloid away. Okay, and that's for number 15. It is always good for you to try to imagine what the solid first. Okay, who knows, we can compute that in easier way. I think number 16 is a good one. It's a very good example. You can do the integration, or once you imagine what the solid look like, you can compute the volume. Just remember one thing. Okay? It is the volume if the integrand is only r. Okay, so in other words, if you have triple integral and then dc dr d theta, something looks like this. This is not representing the volume. Okay, this is not representing the volume of cylindrical coordinate system. In cylindrical coordinate system, only if you have r in there. Of course, it is still a volume for this one. This is a volume if you are seeing this volume, if you are seeing this as a theta rz coordinate system. Okay, but not volume in cylindrical coordinate system. Okay, let's go on, do more problems. This part's supposed to be on the easier side because we already learned the polar part, right? And this is just the augmentation of that. Let's see, number 18 to number 22. Which question you want me to do? Let's do number 18 first. Let's do number 18 first. Evaluate triple integral over domain E of z dv, where E is enclosed by paraboloid. E is enclosed by paraboloid z equals to x squared plus y squared, and z equals to 4. Okay, this is equals to r squared. So c equals to r squared looks like this, and c equals to 4. So this is the solid then, huh? This is the solid. Right? Okay, so when we try to compute that, there will be integral from 0 to 2 pi. That's for the theta. Okay, the radius r will be from 0 to 2, right? Because c equals to 4 when it intersects with r squared, that gives us r equals to 2, right? Okay, now what happened to the z? The z will start from r squared. The z will start from r squared to 4. Okay, then it seems like it's independent of theta, huh? Independent of theta. So there will be the length of the angle theta. So 2 pi integral from 0 to 2. And then when I integrate respect to z, that will be 1/2 c squared r dr from r squared to 4. So that will be 16 minus r to the 4th dr. I wonder if you can follow me. I basically replaced the c in the c squared by 4, that gives me 16. And then by r squared, that gives me r to the 4th. Okay. Thomas, what happened to the theta, Thomas? Well, notice that the inner integrals, both of the inner integrals are independent of theta, right? And then the integrand also independent of theta. So when we integrate later on the d theta, that will be just the length of interval of theta. Okay, of course, just feel free to do it inside out as usual. Okay, but you will see the same phenomena. So this will be pi, 2 and 1/2 cancels, right? Integral from 0 to 2 of 16r minus r to the 5th dr. And when I integrate further, that will give me 8r squared minus 16r to the 6. From 0 to 2, that will be, what's that? 4 squared. 4 times, that's 32 minus 64 over 6, that's 32 over 3, minus 0, minus 0. Okay. So that will be, what is this? It's 64 over 3, huh? 64 over 3 pi. 64 pi over 3. That's for number 18. Number 22. Find the volume of the solid that lies within both. So the solid E is inside x squared plus y squared equals to 1, and inside x squared plus y squared plus c squared equals to 4. Oh, wow. Okay, so this is for r equals to 1, and this is r squared plus c squared equals to 4. What does the solid look like to start with? Well, inside the cylinder, r equals to 1. So this is the cylinder. And inside the sphere with radius 2, something looks like this, approximately, right? So it will be inside the cylinder and also bounded above by the cap of that sphere, and also below by the cap at the bottom of that sphere. Okay, so we are talking about this solid here. This is the top cap, this is the bottom cap, and the lateral the lateral cylinder is this. Okay, that's the skin. Okay, so on the domain, it will be basically a disk with radius 1, right? That's the domain. Okay, and we need the volume. So the volume will be triple integral over E and then R dc dr d theta, right? Okay, the theta will be from 0 to 2 pi. The radius will be from 0 to 1. Okay, and then the z will be from the bottom, which is negative square root of 4 minus r squared. Negative square root of 4 minus r squared to square root of 4 minus r squared, r dc dr d theta. Okay, now then the integrands and the limits of integration is independent of theta. So let me just do this. This guy together with this guy give me 2 pi. Integral from 0 to 1. And then r. Now notice that the inner integrand, this guy here, is independent of the integrand has no z, right? So that's just the length of the interval. Okay, so that will be 2 square root of 4 minus r squared dr. I hope you can follow me. Okay, now then from here is just a regular integration. I do substitution, so u equals to 4 minus r squared So du equals to negative 2r dr. Okay, so we get 2 pi integral from 4 to 3, right? U to the power of 1/2, while 2r dr is negative du. I reverse the limits of integrations so that we can absorb the negative. This is 2 pi times 2 over 3 u to the power of 3/2 from 3 to 4. So that is 4 pi over 3, and then what will that be? 4 to the power of 3/2 minus 3 to the power of 3/2. 4 pi over 3 to cube. That's 8 minus 3 radical 3. Okay. I think the issue here is how you set up the integration though. Okay. And trust me, this is one thing that you cannot get away. You know, I know some of you may think, oh, Thomas, I can always use some software or some app to do problems. No, trust me. This one is not doable as easy. Okay. Because even artificial intelligence, some of them not well trained to do the three-dimensional integrals yet. Okay, at least not now. Years later, you may have. Artificial intelligence is actually like a horse. Like you need to train it to do something. Okay, so at first, right now, you can ask a question right now that they don't have the answer, but years later, after some people train that, then it will be able to answer that. You know. Okay, let me go on further. Number 23 to number 25. Number 24. Let's do number 24. The volume of the solid that lies between the paraboloid C equals to x squared plus y squared, which is r squared, and inside the sphere x squared plus y squared plus c squared equals to 2, which is the same to say r squared plus c squared equals to 2. Okay, so on RC plane, this is R, this is C, it looks like it is between the paraboloid. So inside the paraboloid, I should not say inside the paraboloid. So between the paraboloid, this is C equals to R squared, and the sphere with radius radical 2. This is r squared plus c squared equals to 2. So we are talking about this part here. We are talking about this part here. The thing is, we are not talking about the area though. Remember, this is in cylindrical. So the graph is actually something looks like this. Okay, we are looking for the volume of that blue solid. Okay, first we need to find out the limits of integration, but apparently the theta will be from 0 to 2 pi, right? But how about the limit of integration? In other words, if I project this edge of the intersection here down to the ground, what will that be? Okay, where do they meet actually? Okay, so I need to put them together though. So z equals to r squared, and r squared plus c squared equals to 2. So if I put them together, I get c plus c squared equals to 2. C squared plus c minus 2 equals to 0. So z plus 2, z minus 1 equals to 0, z equals to negative 2, which is nonsense, right? I mean, the c is clearly positive here, and z equals to 1. Oh, they meet at z equals to 1, but when z equals to 1, when c equals to 1, then r squared equals to 1, so r equals to 1. Okay. In other words, then the triple integral for the volume from 0 to 2 pi for the theta, the r will be from 0 to 1. And as for the z will be from the lower bound is r squared. The upper bound will be square root of 2 minus r squared. Okay. Now that will give us, well, again, this guy here will give us, you know what, let me use different color so that you don't confuse that with the blue color I used earlier. This guy will give me 2 pi. Okay, and then this guy here will give me just the length of the interval, right? So that will be square root of 2 minus r squared minus r squared. Integral from 0 to 1 r dr. How to do this? Okay, I think I need to split the integration. So 2 pi times integral from 0 to 1 of r square root of 2 minus r squared dr minus integral from 0 to 1 of r cubed dr. Okay, I think I will just let you do this. Here for the first integral, you use substitution, right? U equals to 2 minus r squared, du equals to negative 2r dr. While this one here you just integrate as usual. Okay. Yeah, notice that the important part is to set it up correctly. Okay. Let's see if there's more questions we can do. You know what? I think let's do number 30. Number 30. This is the last question for this section, by the way. Okay. Notice that we have dz dy dx. Okay, but this is r, right? X is from negative 3 to 3. X is from negative 3 to 3. The y is from 0 to square root of 9 minus x squared. That's actually a semicircle then. This is x, this is y. Okay. So if I change that, it becomes integral from 0 to pi, integral from 0 to 3, right? dc r dr d theta. In other words, this guy becomes this. Okay, I have r here. That's from this. Okay, so notice that we have one r coming from the integrand and another r coming from the change of variable. Okay, now how about the dc? I'm sorry, this should be dc here. How about the dc? It will be from 0 to 9 minus r squared. Okay, that's the setup. Okay, so that will be pi integral from 0 to 3 r squared 9 minus r squared dr. Okay, again, notice that dc here, okay, just the length of interval because the integrand happens to have no z, right? So it will be just the length of the interval. On the other hand, for the d theta, notice that the integrand and all the limits of integration is independent of theta. So this guy here will just give us pi. Okay, and then from there you continue yourself. Suggested homework from here. From this 15.8, do number 1 to number 30, just do the odd ones. Okay, that's for 15.8. Let me move on to 15.9. Oops, what is this? 15.9 is triple integrals in spherical coordinate system. This one is a bit harder to explain because of the following. Maybe we go back a little bit, recall the way we set up double integrals in polar. Double integrals in polar. At that time, we have this case, like the rectangle. When we define the rectangle in polar looks like this. It looks like this. Which of course doesn't look like a rectangle, but when you see that from polar coordinate system, you will see this is our theta 1, this is our theta 2, this is r1, this is r2. Right? Okay. Now suppose this is our small rectangle dA, then the area, the differential of the area is actually the change of the radius. This is the dr. Okay, and the length of this arc here. The length of this arc here is r d theta, where this is the d theta. Okay, that's how we then get that dA equals to r dr d theta. Okay, now what happened then if we have this spherical coordinate system? I need to borrow a picture from our textbook to help us see. Let's take a look on this picture here. So for triple integrals, in spherical. Suppose this is our box here. Suppose this is our box with edges. These are the edges here. Not nice, I know. Sorry. Okay, now this box, which we will call differential of volume, has what kind of measure? Now first, what is the length here? The length here is d rho. Okay. Next, what is the length here? The length here is rho d phi. Rho d phi. Why rho d phi times? Because the change of the angle phi multiplied by the distance from the origin. Okay. The same reason we have here. Exactly the same reason we have here. The length of this arc here is equals to the change of the angle d theta times the distance from the origin, right? Okay, so if we go to this triple integral here, and the length that I mark in red here is the change of the angle d phi multiplied by the distance from origin rho. Okay, now the third part is the hardest to see. It's the length of this part here. What color should I use? Let me use darkening. Okay, this part here. What is the length here? Yeah, the length here is rho sine phi d theta. Now, we have the shadow on the ground. This is the shadow on the ground, right? The length are exactly the same. Now, the length here, this is rho sine phi. Basically, that's equals to r, the radius from z-axis. Okay, so the length here is the length of this arc here, the length of this arc I'm talking about, okay, the one I'm marking yellow highlight, is the distance from the z-axis. This is the distance from z-axis, rho sine phi, times the change of the angle d theta. Okay, so if I collect them now, I have d rho, I have rho d phi, and then I have, let me change that in green, I have rho sine phi d theta. Okay, so my d phi now can be re-expressed as rho squared sine phi d rho d phi d theta. Okay, in triple integral later on, if I have triple integral of integrand f d phi, now this becomes triple integral of E1 f, but I need, once I change the dv into rho phi theta, then I need to insert that rho squared sine phi, rho squared sine phi d rho d phi d theta. Okay, let's do problems. First, as before, suppose we are given a triple integral. Can we imagine the solid? Now, of course, the one we have here may be the easy part only, right? But notice that this rho squared sine phi is actually part of this thing here. Okay, so that's not a real integrand. That's actually the multiplier we get because we changed to spherical coordinate system. But notice that the theta is from 0 to 2 pi, right? And then the phi is from pi over 2 to 2 pi. Remember, what is phi? Angle phi is the angle from positive c-axis. The angle from positive c-axis. This is the phi. Okay, so if the phi is from pi over 2 to pi, it means it's already below xy plane. Okay, it's below xy plane. In other words, this means the c is less than equals to 0. And then the last part, rho, is from 1 to 2. Can we imagine what is this? It seems like it's actually a ball. Okay, let's deal with these two first. It's the angle is, if I draw, this is my z-axis, right? If that's my z-axis, because the phi is from pi over 2 to pi, it means it covers from here to here, right? Okay, but then I need to spin it. It's from radius 1 to radius 2. So can you imagine if we have hemisphere, lower hemisphere with radius 2 with lower hemisphere with radius 1 cut off. Cut away. Okay, so yeah, that's what the solid looks like. How about the volume then? Let's do it with geometry first. The volume, therefore, equals to the volume of the hemisphere with radius 2, lower hemisphere with radius 2 minus the volume of the lower hemisphere with radius 1. Okay, volume of a hemisphere is 1/2 of 4 over 3 pi r squared, r cubed, I'm sorry, minus 1/2 4 over 3 pi 1 cubed. This is 2 over 3 pi 8 minus 1, that's 7. Oh, that's the answer, huh? That should be the answer. So that's 14 pi over 3. Now let's try to compute that triple integral and see if we should get the same result. Now apparently the integrand and the limits of inner integrals are independent of theta, right? Okay, so this will be just 2 pi, and then integral from pi over 2 to pi of, I need to integrate with respect to rho first, so that will be 1/3 rho cube sine phi from 1 to 2 d phi. Is it right? That is 2 pi over 3 integral from pi over 2 to pi of 8 minus 1, that's 7, sine phi d phi. Well, but the area of sine phi in the second quadrant is 1. This is 1, right? You can just integrate it, but then you will get that's 14 pi over 3. Okay, that's for number 18. Let's see more. How to set up integral, maybe number 20. Set up the triple integral of an arbitrary continuous function f x y z in cylindrical or in spherical coordinates over solid shown. For number 20, of course, spherical is better. Okay, so the theta will be from, apparently the theta is not from 0, it's from pi over 2 to 2 pi, right? The radius rho is from 1 to 2. But how about the phi? The phi is from 0 to pi over 2. Huh? Okay, so the triple integral will be from pi over 2 to 2 pi, and then the phi is from 0 to pi over 2. The rho is from 1 to 2 of f rho theta phi rho squared sine phi d rho d phi d theta. That's the setup. Okay. Of course, we cannot integrate this because we don't know what's the function. Let's see more. Use spherical coordinates to integrate this. Let's see number 22. Number 22. Evaluate these triple integrals of 9 minus x squared minus y squared dv, where h is the solid hemisphere, x squared plus y squared plus c squared less than equals to 9, and positive c, non-negative c. Okay. Somehow I think it is easier to do using cylindrical. Let's practice. Suppose I use cylindrical. Then this becomes triple integral. Can you imagine what this looks like? That's hemisphere, the upper hemisphere, right? With radius 3. You see, right? Okay, so 0 to 2 pi, that's for the theta. The r will be from 0 to 3. The c will be from 0 to 9 minus r squared under square root. Okay, and then this is 9 minus r squared, r dc dr d theta. I think it's easier to do it that way. Okay, but this is a cylindrical integral, right? Cylindrical integration. But if we use spherical integration, and then it will be rho squared sine phi d rho d phi d theta, where the theta will be from 0 to 2 pi. The phi will be from 0 to pi over 2, and the rho will be from 0 to 3 of 9 minus, now what is x squared plus y squared? X squared plus y squared is, that's r squared, but r squared in cylindrical is equal to rho sine phi squared. Okay, How do you get that, Thomas? Hold on. X squared plus y squared. If this is C, this is R, right? So this is the same to R. This is the phi, this is the rho, right? Notice that R is rho sine phi. Okay, so this is rho squared sine squared phi. It may not be that nice to compute, huh? So this is in cylindrical. This is in spherical. So we have 9 rho squared sine phi minus rho to the 4 sine cube phi d rho d phi d theta. Again, like what I said earlier, I think it's easier to compute with using cylindrical. But let's just do this then. Let's just do this one. I need to integrate with respect. Oh, it's independent of theta, huh? Okay. So I will have 2 pi integral from 0 to pi over 2. And then 1/3 rho cube sine phi minus 1 rho to the 5th over 5 sine cube phi from 0 to 3 d phi. So that will be 2781. So integral from 0 to pi over 2, that's 81 sine phi minus 81 times 3, 243 over 5 sine cube phi d phi. Okay, I will split this integral because this one is easy to integrate. So integral from 0 to pi over 2 of 81 sine phi d phi, that one is easy to integrate. Integral from 0 to pi over 2 of 243 over 5 sine cube phi. This one, I think I need to do something. Okay, but I know integral from 0 to pi over 2 of sine phi d phi is equal to 1. Okay, you can just integrate it yourself. Okay, so this is 81 minus the things. How do we integrate that sine cube thingy? 243 over 5 integral from 0 to pi over 2, that is sine squared phi sine phi d phi. Yeah, we go back to calculus 2, huh? Uh, 1 minus cosine squared phi sine phi d phi, right? So u equals to cosine phi du equals to negative sine phi d phi. So we get 162 pi minus 486 over 5. Integral from 1 to 0 of 1 minus u squared negative du. It's integral from 0 to 1 of 1 minus u squared du. This is all computation. I'm kind of lazy to do this, honestly. So this is u minus 1/3 u cubed from 0 to 1. That's 2/3. Divided by 3 is what? 162 times 2 is 324 over 5. 324 over 5. Okay, but again, that's just computation, which I do expect you to be able to do yourself. Okay, that's for number what? Number 22. Let's see number 26 then. I randomly pick questions, honestly. Okay, number 26. Evaluate these triple integrals where E, the solid E, lies between the spheres and above the cone. Okay, so if it is between the spheres with radius with rho equals to 4 and rho equals to 2, and above the cone pi over 3. So that's what the solid looks like, huh? Yeah, of course we need to revolve this around z-axis though. Okay, so the theta will be the triple integral over solid E of x, y, z dv now becomes integral from 0 to 2 pi for d theta. The phi will be from 0 to pi over 3 d phi, and the rho will be from 2 to 4 d rho. This is phi here. Okay, and then we have, of course, rho squared sine phi, right? But don't forget the xyz here. The xyz here will need to be something also, right? Okay, where the x is rho sine phi cosine theta. The y will be rho sine. I need to move this a bit further. See rho sine phi sine theta, and then the c will be rho cosine phi. Wow, that's a lot, huh? So many things put together. Okay, let's tidy it up. It's from 2 to 4. How many rows we have? It's 1, 2, 3. That's rho to the 5th. And then sine squared, sine cube phi, cosine phi. And then cosine theta, sine theta, d rho, d phi, d theta. The nice thing about this integral is the domain is a rectangle and the integrands are separable, right? Okay, so we can rewrite this into the product of 3 integrals. So it's integral from 0 to 2 pi of cosine theta sine theta d theta, integral from 0 to pi over 3 of sine cube phi cosine phi d phi, integral from 2 to 4 of rho to the 5th d rho. Right? Instead of integrating all of them, I happen to see that this guy here is equals to 0, huh? Don't you think so? Okay, let's integrate that at least. Let's integrate that. This is integral. If I use u equals to sine theta, so du equals to cosine theta d theta. Is it right? Okay, but the limit for integration becomes 0 to 0. Now you see that? Okay, u du times blah 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 blah, but that's basically equals to 0. Okay, seems to be a hard integration, but the final work is the final result is 0. It's kind of disappointing. Yeah. Okay, that's for number 26. Let's do more. Number 28. I think that's a good question. Find the average distance of a point in a ball of radius a to its center. The average distance of a point in a ball radius a to its center. Let me try to understand the question. Average distance. So average distance. So suppose I have a ball with radius a. Radius is a. So if I pick a point inside that ball, call that x, y, z, then the distance to the center will be rho. Is it right? Now the thing is I need to take the distance of all such points inside the ball and find the average. How do we do that? Okay, so the average is equal to 1 over the volume, right, of triple integral over that ball B of the distance rho times dv. Is it right? By the way, the volume of a ball with radius, in this case a, will be 4 over 3 pi a cubed, which can be obtained by doing this triple integral 0 to 2 pi, 0 to pi, 0 to a, rho squared sine phi d rho d phi d theta. Okay, you will get that now. But this is basically triple integral over b of dv. Okay, now the difference is, now notice that I insert this rho here. Okay, so I will get 1 over 4 pi a cubed over 3 times integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to a, rho times rho squared sine phi d rho d phi d theta. Okay, so this is 3 over 4 pi a cubed times 2 pi times 2. The 2 pi comes from here, as usual. The 2 pi comes from here. But I want you to think a little bit how I get these two. Okay, you think a little bit. And then the inner integral respect to rho, that will be 1/4 of rho to the 4th. So that's 1/4 a to the 4th. Maybe I highlight that too, even though not highlighting that to give you the same result. Okay, so the 1/4 cancel the 4, the pi cancels, the a to the 4th cancel 3 of a cubed, so I have 3a over 4. Huh, is it right? Mm-hmm. That's 3a over 4. So yes, if you randomly pick a point on the this ball, then approximately half of the time it will be 3a over 4 or more. Another half is 3a over 4 or less. That's the average. Okay, let's do more. Maybe I pick one more questions and then I give myself a break. But we have a lot more to work on though. Let me pick what question. Let's do number 40. I think that's a good question. So, given the triple integral in rectangular coordinate system, can we convert this into spherical? Let's sketch that first. The y, notice that dy is from negative a to a. The y is from negative a to a. The dx is from a squared minus y squared. X from, so it's actually a disk, huh? Yeah, a disk. Right? So x is between negative square root of a squared minus y squared to a square root of a squared minus 1 squared. Okay. And then how about this part here? The z. The c is between the square root of a squared minus r squared to negative square root of a squared minus r squared. Whoa, that's a that's just a ball, huh? So because this will give us r squared plus c squared equals to a squared, right? Okay, that's basically a ball with radius a. Okay, not bad. Maybe I write it in a better sense. This is yeah, r squared plus c squared equals to a squared. So in total, that's a ball with radius a. Okay, now how about the integrand? Let me use what color? Maybe light blue color. I can factor the z here. X squared plus y squared plus c squared, that's rho squared. But c itself is rho cosine phi. Okay, now I think I'm ready to do that. So solution, actually the solution starts from there. So that triple integrals now can be expressed as triple integral from 0 to 2 pi, 0 to pi, 0 to a. Right? That gives us a ball with radius a. Okay, and the integrand is rho cubed cosine phi times rho squared sine phi d rho d phi d theta. Okay, and because the domain is quote-unquote rectangle and the integrands is separable, then we can do we can split that into the product of three integrals: integral from 0 to 2 pi d theta, integral from 0 to pi of cosine phi sine phi d phi, and then integral from 0 to a of rho to the fifth d rho. Okay, I think the answer is 0. Yeah, I think the answer is 0. Why? How do we know? This is 2 pi, that one is easy. The issue is here. If u equals to sine phi, du is cosine phi d phi, and I get integral from 0 to 0. Okay, u du, and then 1/6 a to the 6. But that's still 0. That's still 0. Okay. That's for number 40. Anything else? I think that's basically it. Yeah, let me just stop here. Right now is 5:53. I will take a break until 6:05. Oh, I forgot to give you the suggested homework. Suggested homework from this 15.9 is from number 1 to number 41. Just do the odd ones and skip the CAS. CAS stands for computer assisted software, or something with software. Basically you need to graph it maybe. Okay, but when you do the suggested homework, if you see that CAS notation, you don't need to work on that. Okay, let's take a break. Okay, let's start again with 15.10. Now this section is actually on the longer side, so I will break it into 2 lectures. The first lectures here is on the building block. So you may not understand what we are doing right now yet, but once we put them together in the next meeting, I hope you can understand better. Trust me, this section is not easy. So if you find it to be on the harder side, you are very normal. 15.10, change of variables. In triple integrals. And I understand you need to study from that 15.8, 15.9. So I try to keep it not too hard for this time. So let's break it down first, what we need to do in this section. First, there are things we need to do. We will learn about transformation. And we will learn transformation from 2-dimension to 2-dimension in this section. And then from there, we will learn to compute Jacobian, which I will do first right now, and then we will learn to compute uh, uh, compute the integrals. The integral with change of variables. The hard part is actually the first part, the transformation. That requires a long explanation. But because it's hard, so I will start with computing Jacobian for now. Okay, Jacobian. Suppose we are given the transformation x. Suppose we are given the transformation t, where x is a function of u and phi, and y also a function of u and phi. Then the Jacobian, I call that J. The Jacobian denoted by dou xy over dou u phi is defined as the determinant of dou x dou u, dou x dou phi, dou y dou u, dou y dou phi. Okay. Let's do an example. Let's do an example. I pick question from our textbook, of course. For now, you will not understand what I do in relation to the triple integrals or double integrals. But I promise you, the next time we meet, I can explain that even better. Okay, we'll put things together. So let's say we have question number 1 and number 2. Okay, actually we can do 1, 2, 3, 4. We can do 1, 2, 3, 4. But maybe number 2 first then. Number 2. So we see that u is u phi, right? So dou x dou u will be phi, dou x dou phi will be u. Okay, and y equals to u over phi. So dou y dou u will be 1 over phi. Dou y dou phi will be negative u over phi squared. Okay, so the Jacobian J in this case is dou xy over dou u phi is the determinant of phi u 1 over phi u over negative u over phi squared. Now, I wonder if you remember how to compute a determinant. Determinant A, B, C, D is equal to AD minus BC. Okay, please remember this though. So, going back to our questions here, this will be phi times negative u over phi squared minus 1 over phi times u, which is negative u over phi minus u over phi, that's negative 2u over phi. That's the Jacobian for that transformation. Okay, so this is the transformation T. Number 4, we have T is given by x equals to e to the s plus t, and the y is e to the s minus t. Okay, so dou x dou s is it's basically itself, huh? e to the s plus t. Dou x dou t is the same, e to the s plus t. Is it right? And then dou y dou s, that's the same, e to the s minus t. Dou y dou t, this will be negative e to the s minus t. Okay, so the Jacobian, which is dou xy over dou st, will be e to the s plus t, e to the s plus t, e to the s minus t, negative e to the s minus t, with which if we compute, that will give us negative e to the 2s minus e to the 2s, which is negative 2 e to the 2s. Okay, now from here I want to tell you, it's not a secret, but if you took linear algebra before, you know this, that if any row or columns have common factor, we can factor that out. So in this case, we can factor the top column, top row, I mean, e to the s plus t, and on the top it becomes 1 and 1. Okay, the bottom rows, we can also factor it out, e to the s minus t, it becomes 1 minus 1, right? Okay, so when we compute this will give us, e to the s, 2s, right, times negative 1 minus 1. That gives us negative 2 e to the 2s. Okay, again, if any rows or any columns have common factor, we can factor that out when we are computing a determinant. Okay, next, what happens if our transformation is actually 3 variables to 3 variables? So suppose our transformation now is x as a function of u phi w, y as a function of also u phi w, and c as a function of also u phi w. Then our Jacobian, denoted by dou xyz over dou u phi w, is defined to be a 3 by 3 determinant of dou x dou u, dou x dou phi, dou x dou w, dou y dou u, dou y dou phi, dou y dou w, and dou c dou u, dou c dou phi, dou c dou w. Okay, now as for how to compute a determinant, they are, I will show you later on. Okay, but keep in mind that if a column or a row has common factor, you can factor that out. If we look back to, let's say, number 6. Number 6, let me copy that again. Maybe number 5 and number 6. We do 2 questions. Number 5. Okay, so dou x dou u is 1 over phi. Dou x dou phi is negative u over phi squared. Dou x dou w equals to 0. Dou y dou u equals to 0. Dou y dou phi is 1 over w. Dou y dou w is negative phi over w squared. Dou C dou U is negative W over U squared. Dou C dou V is 0. Dou C dou W is 1 over U. So the Jacobian, which is dou XYZ over dou U phi W, is the determinant of 1 over phi negative U over phi squared 0. 0, 1 over W, negative phi over W squared, and then negative W over U squared, and then 0, 1 over U. Notice that for each rows, we have common factor 1 over phi for the first row. Second row, we have common factor 1 over W, and in the last row, we have common factor 1 over U. So I can pick that out. So I can get 1 over phi times 1 over W times 1 over U, and this is 1, negative U over phi 0, 0, 1, negative phi over W, and negative W over U, 0, 1, like that. Okay? Let me put it here. Make it a bit smaller. Okay, now, then to compute that, to compute this, we have a couple ways. We have a couple ways. But the one I like the most is, I don't know, you may want to go back to precalculus, or you search on YouTube how to compute a 3 by 3 determinant. How to compute a 3 by 3 determinant. There are 7 ways. There are 7 ways. Okay. The first 6 ways are basically doing expansion. The one I taught you in at the beginning of this course, we did the first row expansion. Remember the cross product thingy, right? The cross product thingy, we use the first row expansion. So it's basically the following. Let me show you, remind you how to do that. That will be 1 times this determinant. 1 times 1 negative phi over W 0, 1. And then minus negative U phi times the determinant 0, negative phi over W, negative phi over U 1. And then plus 0 times 0, 1, negative W over U 0. Okay, which if we compute further, we get 1 over phi U phi W, and then the first, it will be 1 times 1 minus 0 plus U over phi, that's 0 minus phi over U. Is it right? And then plus 0 times 0 plus phi over U. Why I feel like I make some mistake somewhere? Am I making a mistake? I don't think so though. Why I say I'm making mistake? Because of the following. When I compute this, I get this is 1 minus 1 plus 0, which is 0. That's not really makes sense. Let me check my computation. So far I'm good. Yeah, so far I'm good. Let me do another way. So another way is this. If I have, let's say, A, B, C, E, F, G, H, I, J, the way to compute that, another way, the seventh way to do that is like you copy the first two columns and then we multiply this way, you add. Okay, so you add this guy plus the product of this guy plus the product of this guy minus the product of this guy. Okay, call this this a big pimple there. So that's the third method, the seventh method. Okay, so if I use that method to compute this determinant, notice that the result's supposed to be 0, at least according to my first computation. Okay, so if I copy that, so 1 negative u over phi 0, 0, 1 negative phi over w, and negative w over u 0, 1. If I copy the first two columns, and I do the main product there, that will be 1 plus negative 1 plus 0 minus, this is 0, this is 0, this is 0, minus 0. Oh yeah, that's 0. Yeah, that's still 0, duh. Which is something I don't expect when I compute a determinant, a Jacobian. A Jacobian, as I remember, not supposed to be 0. Well, anyway, that's what I get. That's for number 5. Let's do number 6. So dou x dou u is 0. Dou x dou phi is 1. Dou x dou w is 2w. Dou y dou u is 2u. Dou y dou phi is 0. Dou y dou w is 1. Dou c dou u is 1. Dou c dou phi is 2v. Dou c dou w is 0. So the Jacobian will be 0, 1, 2w, 2u, 0, 1, 1, 2, phi, 0. Okay, let me copy the first two columns. And that's the main product, the product of the main diagonal. That will be 0 plus 1 plus 8u phi w. 0 plus 1 plus 2, 8 u phi w minus the sum of the products of the off diagonals. That's 0, 0, 0. Okay. That's 0 plus 0 plus 0. So this is equal to 1 plus 8 u phi w. Okay. So this number 1 to number 6, basically we learn to compute the Jacobian. Okay. As much as you think this is difficult, this is the easiest part for this section. For this section, this is the easiest part. Okay, let's do the later part, the second part, number 7 to number 10. I will do even number, of course. For odd numbers, you try to do it yourself and then see if you get it right. Okay. Now, find the image of the set S under the given transformation. So what happened is we have set S. Let's do number 8. S is a square bounded by lines u equals 0, u equals 1, phi equals 0, phi equals 1. So on the u phi, u and phi, that's a square from 0 to 1, 0 to 1. This is S. Okay, a very, very nice domain to integrate with. Okay, the thing is we want to transform this into something ugly. Of course, I don't know why we do that, but let's take it by faith for now. Okay, so we will do the transformation becomes x in terms of xy. Okay, using what transformation? Using the transformation that x equals to phi and then the y equals to u times 1 plus phi squared. Okay, so the x is equals to phi, but your phi here is from 0 to 1, right? Because your phi is from 0 to 1, phi is from 0 to 1, and x equals to phi, it means your x will also from 0 to 1, right? That one is easy. How about the y? How about the y? Now this is where it becomes very difficult. Why this section becomes difficult? Because I need you to pay attention to the following. Okay, let's see the details. I will break this square here into 4 paths. Let's call that gamma 1. This is our gamma 2. This is our gamma 3. And this is our gamma 4. Okay, so gamma 1. For gamma 1, y, I'm sorry, the phi equals to 0. The u is from 0 to 1, right? Now under that transformation, okay, under that transformation, the phi equals to 0, so x equals to 0, right? X equals to 0. So phi equals to 0. Now the y will be, notice that phi equals to 0, right? So y will be u. Okay, take a look, take a look, take a look. Maybe I go backward a little bit. Phi, x equals to phi, but phi equals to 0. So from there we get x equals to 0. Right? Now y equals to u times 1 plus phi squared, but we know the phi equals to 0, right? So y equals to u, but we know the u is from 0 to 1. So y will be from 0 to 1. So what happened with this gamma 1? This gamma 1 will travel on x equals to 0, y from 0 to 1. This is the image of gamma 1. It goes that way. Okay, now let's go to gamma 2. Gamma 2, we know the u equals to 1, but the phi is from 0 to 1. Under that transformation, what will happen? Notice that x equals to phi, right? In other words, the x will be from 0 to 1. Okay, but how about the y? The y will be, when u equals to 1, there'll be 1 times 1 plus phi squared. right? Which is basically, yeah, it's 1 plus phi squared. Okay, but what is my phi again? My phi is x. So y equals to 1 plus x squared, right? So what happened then? The image of gamma 2 is this. This is the image of gamma 2. 1 plus x squared. Now, how about gamma 3? Gamma 3, we have the phi equals to 1. The u is from 0 to 1. So under that transformation, x equals to phi equals to 1. That one is easy. Okay. Y equals to u times 1 plus phi squared, but our phi equals to 1. So that's 2u. Okay. Y equals to 2u. But what is u again? Our u will be from 0 to 1. Okay, so y will be from 0 to 2 then. Okay, so our gamma 3 will be this path here. In fact, it will go this way. The image of gamma 3. That's the image of gamma 3. Okay, and for gamma 4, we get u equals to 0, and the phi will be from 0 to 1. Under that transformation, x equals to phi, so the x will be from 0 to 1. And because the u equals to 0, then the y will be 0. Right? Okay. So y is 0, x is 0 to 1. So the image of gamma 4 is this. So notice that I have to do it segment per segment and see what happened. Okay. So this is the resulting image. Now notice that this transformation is converting from something nice, a square, to something not that nice, the S star. Okay, now we can compute the Jacobian for this t though. We can compute this Jacobian t. Okay, but that's not the issue for now. The issue that is harder is what happened to the image. Yeah, what happened to the image? Okay. Let's see number 10. Let's see number 10. We have S is a unit disk. S is a unit disk with radius 1. With transformation t, what will that be if x equals to au and y equals to b phi? It's easy to compute the Jacobian, but what happened to the transformation? Okay, this is u, this is phi. So u equals to x over a, v equals to y over b. So if we have u squared plus phi squared equals to 1, that becomes x squared over a squared plus y squared over b squared equals to 1. That's an ellipse. Okay, with x vertices negative a and a comma 0, and y vertices at 0 comma b and 0 comma negative b. This is the image. Okay, again, to compute the Jacobian is something easy. Okay, let's do a bit more. It's more about killing the time, to be honest with you. But the third part here is actually on the hard part. This is the hard part. On the next meeting, when we put things together, you will see the beauty of these things. Okay, we have region R in xy planes given. Okay, find the equation for a transformation T that maps a rectangular region S to in the UV plane onto R. Here's the thing. What is given to us here? Let's say number 12. Okay, number 12. What is given to us is the region R on xy plane with vertices 0, 0, 4, 3, 2, 4, and then negative 2, 1. So we have this parallelogram. Of course, this is ugly, right? This is ugly. This is our R. The thing is, we need to find a T. We need to find a T, that's the one in question, from a UV plane that comes from a square. It doesn't have to be a square though, it's a rectangular region. Okay, find the T such that you come from a nice rectangle. So we don't know what's the rectangle yet, but we'll find a rectangle using that transformation to get R. Now, the strange thing here is like we know the final result and the final result is ugly. We need to find the transformation from something nice. Okay, let me not use the word rectangle, but let me use the word S. Okay, find the rectangular S in UV that is nice, such that after certain transformation T, you get an ugly parallelogram R, which is kind of strange, right? When we do plastic surgery, we're supposed to get something nicer. Okay. Now, another way to think about it is like this. Okay. I think the next thing is the leap. Okay. Can you think of a transformation backward? I use T inverse now. So I start from that parallelogram R and do some transformation. Now we call that T inverse to get a nice rectangle S. Okay, I think we better say it that way. Okay, now how do we do this? What we need to do, actually, we need to find the equation of each segment of that parallelogram. Okay, so this is 0, 0. This is, what is this? This is 4, 3, huh? This is 4, 3. So we can say this is y equals to 4 over 3x. Is it right? Is it right? This is what? This is 2, 4. This is negative 2, 1. So what is the equation here? This is y equals to, this is y equals to 4 over 3x plus what? Plus something. Let me see. 2, 8 over 3. And I want to get 4. 4 over 3. Am I okay? Hold on. Let me check something. 2, 8 over 3. 8 over 3. I need to get 12. 4 over 3. Oh, so I think that's correct. Yeah, let's do it this way. 2 comma 4 and negative 2 comma 1. Okay, so the slope is 4 over 3, so y equals to 4 over 3x plus constant b. When I plug in 2 comma 4, 4 equals to 4, 3 times 2 plus b. So this is 12 over 3, this is 8 over 3, so the b is 4 over 3, that's right. Let me check. So 1 equals to 4 over 3 times negative 2 plus b. So 3 over 3 equals to negative 8 over 3 plus 4. Something not right there. Ah, what am I doing? The slope is 3/4. Duh. The slope is 3/4. No wonder. Yeah, the slope is 3/4. What am I doing, right? The slope is 3/4. So y equals to 3/4 x plus, if I put 2, that will be 3/2, 2/2. Okay, so this line here is 3 over 4x plus 5/2. This is y equals to 3 over 4x plus 0, or just 3 over 4x. Now, and then let's see this part here. This is y equals to negative 1/2 x. Is it right? While this part here is y equals to negative 1/2 x plus 5. Okay, so I can now do this transformation. Let's see. I will call this 1/2 x plus y equals 0. This is 1/2 x plus y equals to 5. And this line here is 3 over 4x minus y equals to 0. This is 3 over 4x minus y equals to 5/2. Okay, so notice my 1/2 x plus y will be moving from 0 to 5. Is it right? No, 0 to 5. While my 3 over 4x minus y will be moving from 0 to 5/2. Okay, let's call one of them u and the other one v. Okay, so my t inverse transformation, u equals to 1/2 x plus y. The v is 3/4 x minus y. Okay, but we are clear that our u will be from 0 to 5, 0 to 5. Our v will be from 0 to 5/2. Okay, so notice that we get the image of R already. From R going back to S, we get that nice rectangle. Okay. The problem is, this is T inverse though. T T inverse where the input are x and y's, the output is u and v. The T that we are looking for supposed to be x equals a function of u and v, and the y will be a function of u and v. Now the thing is, how do we get this? Well, we solve that then. Okay, we solve that then. For example, one thing we can do is, if I add this, I will get, if I add that, I will get, what's that? 5 over 4x equals to u plus v. So x is 4/5 u plus 4/5 v, right? Okay, so this is 4/5 u plus 4/5 v. Now, if I need to solve for y, then I plug that x in to either one of them. So u equals to 1/2 x, and then solve for y. That's 2 over 5 u plus 2 over 5 v plus y. So y will be 3/5 u minus 2/5 v. Okay, that's my t. Now remember that at the earlier part here, we actually learned to find the Jacobian. Okay, now it's time for me to show you how the Jacobian of transformation t relates to the Jacobian of transformation t inverse. Okay, now let's see. The Jacobian of t will be 4/5, 4/5, 3/5, negative 2/5. That is negative 8 over 25 minus 12 over 25. That's negative 20 over 25. That's negative 4/5. How about the Jacobian of t inverse? Basically, you do the derivative of the partial derivative of u respect to x and y, partial derivative of v respect to x and y as well. That will be 1/2, 1, 3/4, negative 1. That will be negative 1/2 minus 3/4. That's negative 5 over 4. In other words, Jacobian of t is the reciprocal of Jacobian of t inverse. Okay, maybe I say that in general, Jacobian of t is the reciprocal of Jacobian of t inverse. Now, take a look on how I do this though. Okay, so basically the way I did it, I get the boundaries of that R, find the equation, and see if they have some consistency. Notice that when I put the x and y terms on the same side, okay, they happen to have the same expression. So call that the u, or in this case it's the u. And when I move the x and y terms on one side, we have the same expression, right? I call that phi. You see that? Okay, so that's how we will do it. Now let's see number 14. This will be the last part for today, number 14. We have R bounded by hyperbolas 1 over x, y equals to 1 over x, and 4 over x. So this is y equals to 1 over x and 4 over x. Y equals to 4 over x. And then the lines y equals to x and y equals to 4x. Now, remember what we want to do. So this is the r, right? This is the r here. Now, what we want to do is to find the u phi that bound this r using nice numbers. Okay, notice that if I rewrite this, I get xy equals to 1. This is xy equals to 4. Let's call our xy now our u. Okay, and here y over x equals to 1, y over x equals to 4. So let's call y over x our v. Now this is our t inverse. Okay, but now we know that our u will be from 1 to 4, and our phi will be from also 1 to 4, huh? Our u is this, and our phi, not a nice one, our phi is this. No, I don't want to use that color. Use another color. Maybe use this one. Still not good. I need a lighter one. Maybe this guy. Yeah, this is better. Right? Okay, so our S right now is, our S is a square 1 to 4, 1 to 4 on u phi. Okay, now how do we find the t, the transformation t instead of t inverse? Let's see. Notice that u times phi give us y squared. U phi give us y squared. So y will be square root of u phi. Supposed to be negative square root of u phi also, but because of the first quadrant, we only take the positive branch. Okay, now u over phi, however, u over phi give us x squared. So the x will be the square root of u over phi. That's the transformation t that we want. Okay, now out of curiosity, what happened to the Jacobian? Okay, Jacobian of t inverse, let's take a look. Jacobian of t inverse will be respect to x, that's y, respect to y, that's x, respect to x, that's negative y over x squared, respect to y, that's 1 over x. So this will be y over x plus y over x, that's 2y over x. How about the Jacobian of t? The Jacobian of t will be respect to u, that will be 1 over 2 square root of u phi. Respect to phi, that will be square root of u to the power of negative 1/2. Negative, that's 3 over 2. Hold on. I'm kind of a bit lost. U to the 1/2, phi to the negative 1/2. When I do the derivative negative 1/2, I'm not integrating. Let's do the derivative. Negative. This is negative square root of u over 2 square root of phi cubed. Now the y that will be 1 over square root of v over 2 square root of u square root of u over 2 square root of v. When I compute, I will get 1 over 2v plus 1 over 2v. I'm sorry, 1 over 4v. 4v, so this is 1 over 2v. Are they equal? No, they are not supposed to be equal, but we know that it's supposed to be Jacobian of t, supposed to be 1 over the reciprocal of Jacobian of t inverse, right? So the inverse of this is x over 2y. You see, right? But y over so maybe we write it this way. This is equal to what is y over x? Y over x is v, huh? So this is 2v. Now you see the reciprocal, right? In other words, for us to find the Jacobian of transformation t in future, we can compute that from the Jacobian of t inverse. Okay, we can compute that from the Jacobian of t inverse. Now, let's see, suggested homework from here. I hope I don't make it too hard for you yet. This is section 15.10. I would like you to do number 1 to number 14. Try to do all of them though. Okay, that's for today. So long.